So we have a new unit of kinetics that we're starting here, and yesterday you guys read a little bit about, or listened a little bit about kinetics and rate laws. So I wanted to do a demo for you, a kinetics demo. So I have two colorless solutions here, solution A and solution B, that we're going to mix. So I'm going to mix them in here. You have to keep your eye on the flask the whole time. So watch the flask carefully. And okay, watch the flask. Are you watching? Oh. You see that? This is called the iodine clock reaction. And so what this is a reaction using starch and iodine, and we're going to use this in lab next week. And we're going to do a lab on the iodine clock reaction as well later. And so we have a series of things that happen, and when we have an excess of iodide ions, it binds to starch and it makes this blue complex. And they call it the clock reaction because we can actually set a clock to it, and we can time things, and based on the time of the reaction, we can determine the rate law. And so depending on the concentration of each of my reactants, that affects the rate law, like we learned in the lecture yesterday. So I tried to glug equal amounts. So now I'm going to try to glug unequal amounts now, right? So I'm just going to pour in, and this is not being measured, of course. So I'm going to pour in maybe B a little bit faster than A. And we'll see if it changes the time that it took for the reaction. And so again, keep your eye on that. So we can change the time of the reaction based on the concentration of the reactants, and that's what we're going to study in lab next, not this coming week, but the week after when we do this. And so studying this kind of stuff and determining what the rate law is what kinetics is all about.
You also change the time by shaking it less?
You technically can, yes, because one of the things that affects reaction rate is the contact between the reactants, right? And so the faster they're moving, the faster the reaction rate. Stirring in general doesn't add kinetic energy though, right? Unless I'm Superman, like this. So when I stir things, I'm not giving it kinetic energy, I'm just allowing the reactants to mix with each other more quickly and touch each other more quickly. And one of the things that you guys are going to study in the lab when you do this, you're going to stir everything with a toothpick because we're going to do it in a well plate. And so your stirring has to be really consistent so that that isn't a variable that affects the reaction rate. But yeah. Okay. So yesterday, when you guys looked at the lecture that I left for you, we talked about a simple rate law, an differential rate law, and then we're going to talk about an integrated rate law. And I showed you one way from data to come up with the rate law. I want to look at that same example that I worked again and use the logic way instead of the math way to figure it out. Okay? So let's take some notes and let's see about the rate law. What we looked at first was what we call the differential rate law, which is rate as a function of concentration. And it has this form where rate is K, which is our rate law constant, times the reactant raised to some power. If we have multiple reactants, so if I have two reactants, then my rate law will have both reactants in them, each one raised to some power. And this power here is called the order of the reaction. In this case, my reaction is nth order, or it's nth order with respect to A. But here my reaction is n plus m order. Okay, so we're going to look at that back with the example that we did before. So I had an example for you guys. Where is our textbook? Here. So we looked at this data here, right? Dun dun. Okay. So we looked at this data and we used a mathematical method to find the rate law. And so we compared the rate of reaction 1 over the rate of 2, and we canceled some things out and found out what the exponents were, right? But we can look at this and do it without having to solve the math in a logical way. Okay, so again, our rate law is going to be of the form so this time it's going to be ammonium. We're having technical difficulties. There we go. To the N, and nitrite. Really does not want to. There we go. All right. If you notice here, between reaction experiment 1 and experiment 2, I have held the ammonium constant. So that concentration hasn't changed at all. But if I look between reaction 1 and reaction 2 here, the concentration of the nitrite has doubled. Yeah? So if this is constant, it can't affect the rate. If this is doubled, how did it affect the rate? What happened here to the rate? It doubled, right? And so if this doubled and this doubled, therefore it must be first order with respect to the nitrite. So do you see how I figured that out without doing all the math? I can just look at it in a logical way. So therefore, it's first order with respect to the nitrite. Then I can do the same thing. And if you design an experiment well, then you run very few trials to get all of your data, and you don't have to waste your time. So here in trial 2 versus trial 3, I can see that this has been held constant, the nitrite concentration has been held constant, but I have doubled the concentration of the ammonium, right? And so that one's been doubled, and so what happened to the rate between trial 2 and trial 3? It doubled as well. And so therefore, if this doubled and this doubled with this held constant, my rate must be first order with respect to the ammonium. Does that make sense? Okay. Now this is a really simple example and doesn't always come out to be first order for both, right? But this is just a beginning example of that kind of thing. So when you design an experiment, when you do your iodine clock reaction in a couple weeks, you want to design an experiment so you have a baseline, and then you vary one concentration. And then for the next experiment, you vary a different concentration, and but keeping everything else constant, right? So we only want one variable changing at a time. So my overall rate law that I get for this is rate equals K times the concentration of the ammonium to the first, and again, we don't write ones, the nitrite to the first. This is a second order reaction overall. So we add up all the exponents, and that's the overall order of the reaction. So this is an overall second order rate law. Everyone okay? Questions about doing that?